Number 62. So we have a 2.6 Newton metal bar. So that is the weight of it, because it's given in newtons. Convenient. It is 0.85 meters long. So 0.5 meters. And it has a resistance of 10 ohms. So that's this bar here. It's a big old resistor. Sweet. It rests horizontally on conducting wires connecting it to the circuit shown. The bar is in a uniform horizontal 1.6 Tesla magnetic field and is not attached to the wires in the circuit. So it's just resting on top of these little bars. What is the acceleration of the bar just after the switch S is closed? So our battery is 120 volts. This resistor is 25 ohms. And this one is 10 ohms. All right. So we have this bar, which is a big old resistor, as part of this circuit. So this circuit is behaving like that bar is just a resistor. Okay? So because this bar is in a magnetic field and it has some current going through it, it's going to feel a magnetic force. So we need to figure out how much current is going through that branch. So we can find the value of that force and therefore get the acceleration. So I have my battery. It's 120 volts. I got 25 ohms up here, 10 ohms here, and 10 ohms over here. So first I want to find my equivalent resistance. So these two dudes are in parallel, which means I add their reciprocals. So 1 over 10 plus 1 over 10 is 2 over 10. Flip it over. That's 5 ohms being drawn from there. So now my 5 ohms is in series with my 25 ohms. So my equivalent resistance is 25 plus 5, which is 30 ohms. So from V equals IR, the current that entire circuit is drawing is 120 volts over 30 ohms, which is 4 amps, not 40, 4. Is 4 amps. Okay. So I have 4 amps coming out of my battery, going through this dude, and then it gets to here. Because these are equal, they are going to equally share the current. It's only because they are equal that they share it. So the current through the bar is 2 amps. So now, from our beautiful picture, our conventional current comes out of the plus and goes this way. So my current through this bar is that way. So the force that this bar is going to feel is IL cross B. But because our bar is perpendicular to our magnetic field, we can just write that as IL times B and use our right hand rule to get the direction. So our first vector is IL. That's pointing this way. Our second vector is our B. I'm going to have to rotate this because my hand can't bend that way. So IL cross B. B is into the page. So our force is going to be this way. So our force is going to be to the right. Alright. So my force, just like last quarter, if I have a force, it's causing some acceleration, ma. Okay. So, we have a force from our magnetic field. It's going to feel it to the right. That's equal to ma. Alright. So they don't actually give us the mass of the bar. They give us the weight of the bar. So our weight is equal to mg. So the mass of the bar is the weight over g. So this is going to be ILB equals the mass, which is the weight over g times A. So A is equal to ILB times G over the weight. So the current is 2 amps. The length is 0.85 meters. My magnetic field is 1.6 Teslas. Gravity is 9.8 meters per second squared. And my weight is 2.6 newtons. So the acceleration that this dude is going to feel times 1.6 times 9.8 divided by 2.6. It's going to be 10.25 meters per second squared to the right. Huzzah!